now that we've seen the fundamental identities, we're going to be using them in different circumstances. One of these is using the Pythagorean identities to evaluate some new trig functions. And in this one, we're supposed to be finding secant and cosecant if the tangent is 3 and the cosine is greater than 0. Or if both the tangent and the cosine are positive. That only occurs here in quadrant 1 where everything is positive. So we need to keep that in mind as we're doing this problem. If we are looking for secant and we already have tangent, then a really great tool to use is one of the Pythagorean identities that 1 plus the tangent squared is the secant squared. And you may want to have the other identities close by so that you can look at them. We need, so then 1 plus 3 squared equals the secant squared theta. And that all together is 10. And that is our secant squared. Therefore, our secant value is the square root of 10. Again, we don't have to worry about this being plus or minus. It's just positive because we are in the first quadrant. Now to find the cosecant, we know that 1 plus the cotangent squared would give us the cosecant squared. And we know that the cotangent is the reciprocal of tangent, so we're using a reciprocal identity as well. So that's 1/3 squared is our cosecant squared. So that means that our cosecant squared is 9/9 plus 1/9. So altogether that is 10/9. And take the square root of both sides, and we have the square root of 10 over square root of 9, which is 3. So there's our cosecant of theta. Now this one uses some of our cofunction identities and a little bit of even and odd identities. So we're starting out with the cotangent of negative theta, finding the tangent of theta minus pi over 2. Now notice that this is a little bit different. The identities that we had for cofunction had pi over 2 minus theta. These are simply opposites of each other, and we will have to be using that fact here in just a minute. Alright, so we're going to start with this, the fact that 7.89 is the cotangent of the opposite of theta. Well, the cotangent of the opposite of theta is the opposite of the cotangent of the positive angle, so just regular theta. That means that it's the opposite of, and now we replace this with the fact that it is the same as the tangent of pi over 2 minus theta. That was a direct cofunction identity. And now we need to start looking at that. We're really close, except that they are opposites of each other, what we're taking the tangent of. So what we're going to do is take out within that function, take out a negative sign there, factor out a negative out of this guy. So this would mean that that would be theta, and we can make that minus pi over 2. If you multiply that back in, you'll get the same thing that we had here. So now we have a negative value inside our tangent value, so it's the opposite of this angle. Therefore, we're going to use another one of those even and odd identities. And that gets us, because there's a negative here and the negative here, they complement each other with those cofunction and even and odd identities, so that this is simply the tangent of theta minus pi over 2. And therefore, we have that 7.89 is equal to the tangent of theta minus pi over 2. There's a lot of different ways to approach this problem, and we had to use multiple identities, including the even and odd and the cofunction identities. But one of those strategies there, especially when you see things like this, is to factor out a negative and use that with the other identities. Okay, another thing that we can do is simplify expressions. This is going to be a very necessary part of what we do. Blue here. All right. Now, when I see this, I immediately am drawn to this tangent squared of x and plus 1. And I recognize that from my Pythagorean identities, that's simply secant squared of x. That's over 1. And if I've got a secant down in the denominator, that means that I'm really working with a cosine. 1 times cosine squared, or just plain old cosine squared of x. So from here to here, we used a Pythagorean identity, and from here to here, we used a reciprocal identity. Now, another strategy that we use quite a bit is to put things back into sines and cosines, especially when you see cotangents. So the first thing I'd like to do on this one is replace that cotangent with cosine of u over the sine of u. And then I get to multiply that by the sine of u. And doing so gets me simply the cosine of u, and it is simplified. Okay. Now the last one, 1 minus the cosine squared. This one is not a direct identity, but it is kind of a descendant of one of the Pythagorean identities. When you have sine squared of an angle plus cosine squared of an angle, we know that equals 1. Well, now I can manipulate this so that it looks like my numerator down in this area. So if I subtract the cosine squared in this, let me fix that. If I subtract the cosine squared, I have 1 minus cosine squared theta. So that numerator can be replaced with what is equal to sine squared. Put that over the sine of theta. And whenever you have a square over the first power, it simplifies down to 1, so that it equals the sine of theta. On to the next piece here, using identities to simplify some expressions. Here we have both probably some Pythagorean identities and perhaps some even and odd things going on here. This right here is exactly the same as taking the secant of the opposite of x squared. That square we just write in there out of habit, and we don't have to have as many parentheses around everything. It's the square of the secant value, not the square of the angle measure. Okay, and then just minus tangent squared of x. That also means the quantity of the tangent squared. And then looking carefully in here, with secant values, that's related to cosine. So that means that the secant of the opposite of x is actually the same thing as the secant of x, that quantity squared, minus the tangent squared of x still. And we see right here, secant squared of x from our Pythagorean identities is simply 1 plus the tangent squared. And then we're going to be subtracting that tangent squared still. And you can see there that we subtract those and we end up with just 1. So we're able to simplify this one to simply 1. Down here at the bottom, we've got some addition going on in here. And I say I've got tangent and cotangent. One strategy for doing this would be to simply change them all into sines and cosines. But this one might prove to be a little easier with a different route. If I have this as 1 plus tan, I could write this one, this cotangent, in terms of tangent. It's 1 plus the tangent, 1 over the tangent. Myself. So this is 1 over the tangent of x. Now, it would be nice if we didn't have a denominator like that. And we can actually rectify that situation by simply multiplying the top and the bottom by the tangent of x. And When I do that, I'm going to distribute on the bottom, but not necessarily on the top. And sometimes you don't know the benefit that you've already done some time. This is going to be 1 plus tangent of x times the tangent of x over, I'm going to distribute that to here and here. So this is the tangent of x plus 1. And now you might be able to see exactly why we did that. I have the quantity tangent of x plus 1 here, and I have the same quantity as a factor in the numerator as well. They divide to 1. Therefore, we are simply left with the tangent of x. Right now we're going to simplify this as much as possible, looking at each piece, and going to get it to a basic trig function. Usually we'll simplify down to just a single thing. Sine, there's not really a whole lot you can do with. Tangent, well, we can replace that with sine over cosine. So this is the sine of theta minus the sine over the cosine times the cosine. And it would be nice to have everything in the same angle. So the cosine of pi over 2 minus theta, we learned with our cofunctions that that is the same thing as the sine of theta. So sines are looking pretty prevalent here. Cosines are going to simplify to 1. We have a sine minus the sine, which will give us a 0. And then we add sine, simply the sine of theta.